into the construction funding going forward from there. Just very briefly, the aperture arrays, for anybody who's not aware, in the case of a dish, you're concentrating the incoming electric field into one place using parabolic dishes which align all the phases to form up a single beam. And what's so attractive about aperture arrays is that, first of all, there's no moving parts. It's an entirely electronic affair. And you have a lot of little receivers, as I mentioned earlier. And by providing the relevant delays between each of those receivers and then adding it up, you form a beam in a particular direction. And the really nice feature about an aperture array is that you can do that as many times as you like, and therefore you can form as many beams as you like on the sky. And that's just limited by the amount of processing and communications you have available. And that means that you can actually observe a great deal of the sky in one go. And since the SKA is primarily a discovery instrument, you want to see as much sky with as much sensitivity in one hit as you can. And that, as I say, is ideal for aperture arrays. Moving into the overall system design, and this is maybe where it gets interesting for people on the processing side of the piece. On this overall system diagram on the left, you've got 3 different collector types, which in the case certainly of the aperture arrays, there's a great deal of processing that takes place locally, which forms up the beams, and that for each of those arrays we're talking of order 10 petamax, since it's a DSP type array. Coming out of each of those 250 arrays, we're anticipating something like 16 terabits a second of data. The dishes have rather less processing involved, but nonetheless produce quite a lot of data and a lot of elements. And that's combined in the central processing facility, which may well be split between the core site out in the desert and transmitting data into somewhere more convenient in the local city, be it Perth or Cape Town. The first step of that is a correlation process, which literally correlates every pair of collectors of a particular frequency and type. That becomes quite a big affair in the case of the SKA, since there's a lot of dishes, for instance, and the correlator goes up is n squared device. Clearly, in the case of the aperture array, you can parallel that up because you've got a lot of beams. From there, the post-processing that gets involved in gridding and forming the image takes of order an exaflop to do for a full SKA, so we're looking at algorithms for that. And the expectation is that we would use the so-called UV processors, which have to buffer several hours of observation so that you can cycle through those observations 4 or 5 times to improve the image quality. And each of those followed up by a substantial amount of processing, which is then combined in what could be regarded as a regular supercomputer, maybe of about 10 petaflops. Bearing in mind that one of those will only be built in the course of next year, probably, that this will represent one of the largest processing facilities on Earth. This is then archived in some way in a massive data archive, keeping the processed data, since there's no way you can keep unprocessed data, and the science is done from that. These are just a couple of illustrations of developments on the aperture array. On the left and the top, there's an actual array, so-called LOFAR, which is being built in the Netherlands. And beside that, in Brace, is a prototype of the higher frequency aperture array, showing a few thousand elements just to get the feel for getting the costs and power right on this. In this one, it's illustrating the kind of technologies that we're interested in at the element level for the low frequency device. it would be very nice, given that these things are separated out by 1.5 meters or 2 meters or so, to have an element that make them self-contained so that you only have fibre optics coming off it and some clocking coming off it. So if you could get each of those to be solar powered with its local power storage and local processing, then it would make deployment a great deal easier and avoid the radio frequency interference problems that might come about from a copper-based connection pattern. And bearing in mind that out in a remote desert to avoid people and RFI, that's obviously an important thing to do. This is illustrating an ideal digital signal processor. It needs to be programmable. It needs to have something of order 20 terabytes of individual chip performance. Ideally, we would integrate the DSKTs, the analog to digital converters, on the chip to save the amount of power required to communicate that data from an ADC into a processor, which is really quite significant. But power is a huge issue for us on this device, since you end up with a great deal of signal processing and you end up with a great deal of elements. And in order to make it affordable in an ongoing sense for the power, we're expecting to restrict the total power requirements to about 100 megawatts, which is a lot, but tough to achieve as it happens. And this slide is illustrating the build-up of the power requirements for an individual aperture array, and even then it comes out at something around 120 kilowatts. Bearing in mind there's then 250 of these arrays, this is really quite substantial. And it does require a great deal of processing and the communications requirements, and you get the budget that's required. So we're building up the requirements of the electronics for this thing. In the central processing, this is zooming in onto that correlator, a monster data switch, these so-called UV processors that each one buffers around 20 terabytes of data and gets followed by a 50 teraflop processor, and we might need something of order 10 or 20,000 of those for this device. And this kind of lays out an idealized UV processor blade requirement. This is an individual processing element on one or two per circuit boards. Each slice may be 1 U high. And that's scaling the processing performance that you currently get out of GPUs and some forthcoming multi-core processors. It's illustrating the buffer store required and actually the speed that's required, because clearly you have to be able to write the incoming data fast enough, maybe more importantly read it 5 times as fast to be able to get that out, and to keep that within a reasonable power envelope of about 500 watts. From that we can derive, through a lot of other conversation as well, a kind of technology shopping list of what we would like to have available for us post-2017. This is for the full phase 2 of the SKA, which is obviously much more challenging than the 10% device. But all of these requirements do appear to be achievable by looking at the different industry roadmaps, discussions with major industry players, and so on. And at that point, I think it's probably worth me just sort of breaking off it here, because otherwise I'll use far more than the half hour allocated. And maybe, Mahisha, this is a good point if anybody's got any immediate questions. Mahisha, is it, how do the questions take place? So it's an exciting, if anybody's got any questions, I'm more than happy to answer any at this point, since I think we're coming close to the end of our webinar here. And it's a very, very quick overview of what the SKA might be, but the key elements is that it's got a huge amount of IT infrastructure. It does require input and work from many industrial concerns and a great deal of software, obviously, to put this thing together.
Hello there. Can you hear me?
Yes. Hi.
Oh. Yeah, so Robert Elliott, National Physical Laboratory in the UK. It's such an exciting project. But, well, the main question I had to start with was, is there a supply chain in place to deliver this project for the Phase 1 construction? I was just interested to know who the Tier 1 suppliers are and how we can get involved with industrial input.
Right, it's being put together in the course of 2011. The current project is working obviously on developments and making sure that we've got the specification of this right. But the so-called pre-construction phase, which is being negotiated by the various funding agencies, even as we speak actually, is scheduled to start in 2012. And that's expecting to put together a consortia to deal with the major individual parts of the SKA, so for instance the aperture arrays, the dishes, the central processing, communications and so forth. And those consortia be led by academia, but absolutely require input and partnership from industry, and it'll be at that point, well, in the course of 2011, that we'll be starting to put those together and to get the developments right through for 2016.
Thanks, Andrew. That's great. Thank you.
Are there any other questions? Okay, well, feel free to send me an email if you have any further questions on the SKA. I think it's at a very exciting stage in the sense that we've gone through 15 years probably of incremental development and thinking about this thing, and it's finally coming to the point that we're setting about serious specifications and serious work that will lead to construction starting in 2016 and very major construction starting in 2019. And it's backed up by most of the funding agencies around the world. And maybe it's worth commenting at this point that the UK has taken a very strong lead position in this with our funding agency, STFC, sharing the funding agencies group, and indeed the international office is currently based in Manchester, and ideally will be staying in the UK 2012 onwards. Okay, Mahisha, do you want to do this thing down there?
Hello, am I audible now? I think I was not audible.
Ah, right. No, I wasn't hearing you till now.
Okay. There seems to be no more questions, and I had just one quick question from my side. What can the UK businesses expect to start off with in the short term? This looks like a long-term project.